Hey everyone and welcome back to PrepFusion. So today we'll start the lecture 2A of this electrostatics chapter. So up until now we have learned what a charge is, how does a point charge experience force according to Coulomb's law. We have learned superposition principle of Coulomb's law. In today's lecture we'll learn about a new topic, that is electric field intensity. Basically, what is electric field intensity and what are its effect, that we'll understand, and we'll also understand the electric field caused due to different finite charge distributions. I taught you a few finite charge distributions like line charge, surface charge, volume charge. So that thing we'll learn here in this lecture, electric field due to different finite line charge distributions. Today we'll start only line, and in the next lecture we'll study about surface and volume charge. So what is electric field intensity? An electric field is the region surrounding a charge object in which another charge experiences a force. So basically, let's say I have a positive charge and I actually bring another positive charge, or any charge, okay, a positive charge, negative charge. If I bring it another positive charge near its vicinity, then vicinity means near its surrounding, then this positive charge will actually experience a force. This positive charge will actually experience a force, and due to which it is experiencing, due to the electric field of this first charge, initial charge, which I cannot see, I cannot observe, but I can experience the force. So I can see the force, because if force acts, the body starts moving, the charge particle starts moving, but I cannot observe the field. So I can't observe, but can feel. How can I feel? Because a force is acting on me. It is either attractive in nature or repulsive in nature. So a force acts on me, okay. I can only observe, I cannot observe the field, I cannot see the field, but I can feel a force, okay. So that is what an electric field is. The electric field intensity represents the strength of this influence at any given point. So how much strength is there? Intensity means what? How much intense is that thing? So if I place this object here, due to this particular lines of force, it will experience some force, right? If there are multiple more lines here, so it will experience more force. The electric field is more intense. That's why the electric field intensity comes that's why it is named like this. It signifies the strength of the force that a test charge would experience due to the presence of a source charge. So basically, what is the strength of the force? Basically, the Coulomb's law, right? Coulomb's law. How much force does a charge experience due to the initial charge? Okay. So talking about the Coulomb's law only, but in different language. So that actually tells us about the electric field intensity. Okay. So yeah, this is done, and yeah, this is this one only. Let me just do this correctly. This is not. It's a bit tilted, and that's the problem. Okay, fine. So when a small test charge, so we place a test charge near a place where we actually want to measure the electric field intensity, and the force that it experiences is basically the electric field intensity at that particular point. The force that test charge experiences at that point is the electric field intensity, which will be independent of this test charge. That I will discuss. How is it independent? I will discuss about that. Okay, don't worry about that. However, the electric field exists even if the test charge is removed, indicating the field is due to the source charge alone. So for us to see the effects of electric field intensity, we had to place a test charge near this. Okay, why is this tilted? I don't understand. Now is this fine? Yeah. So I have to place this test charge near this positive charge, but the thing is, if I even remove this test charge, right, this electric field will still remain, although I cannot see. I can see lights and all those things, but I cannot see the electric field intensity. So that is one drawback. Okay. However, the electric field exists even if the test charge is removed, indicating that the field is due to the source charge alone. Okay. So that is one thing. The closeness of the electric field lines indicate the strength of the electric field. So if the field lines are very, very close to each other, just like here, if they are more closer to each other, it will be more intense. As there are more field lines, it will experience more force. Okay, get the point? The tangent to the field lines at any given point gives the direction of the electric field at that point. Okay, so the tangent of this, right? So let's say I want to find out the direction of electric field at this point. It will be the tangent, right? Tangent. Okay, just touching the curve. Here, what is the direction? Tangent of this. Okay, so basically the direction of electric field gives the direction of the force that the test charge will see. Okay, it will direction that the force it will receive. Okay, that is a test charge. No two electric field lines can intersect. So one thing, there is a property of electric field that no two lines, right, can intersect. Why it can never intersect? Because if the two lines intersect, right, then the direction of force will be ambiguous. Direction of force will be ambiguous. What do I mean by this? I'll just explain in a bit. Okay, it will be ambiguous. So if it is ambiguous, what does it mean basically? So here, let's take an example. Let's say my electric field lines are coming like this and coming like this. Okay, I have two electric field lines, right? These two are intersecting. Now this at this point, this electric field line is telling me that the electric field intensity direction should be this, but this field line is telling me that the electric field intensity line like direction of electric field intensity should be this. So at the same point, the direction of electric field intensity is different. That is not possible. Not possible. Direction, like the electric field intensity can only have one direction. So that's why electric field lines can never intersect each other. Okay, I hope you understand that point. Electrostatic interaction between charged particles is a two-step process. First, like I told you, that two charges actually experience a force known as Coulomb's force, according to Coulomb's law. But first, what happens is that it is a two-step process. First, if I have two charges, right? Just hold on a second. As I was talking, the force between charge, right, is a two-step process. First, the charge actually generates the electric field. Both the charge generates the electric field, and the electric field due to the other charge will actually generate a force in the other charge. Okay, so basically, if I take example, here I have Q1 and Q2. Now this will generate, Q1 will generate some electric field, right, and Q2 will generate its own electric field. Okay, so due to the electric field of Q1, this Q2 will actually experience a force, and due to the electric field of Q2, this Q1 will experience a force. Okay, so this is how the force actually happens. Not that simultaneously like Q1 and Q2 are placed and simultaneously forces are getting acted. No, it's a two-step process. Okay, first field gets generated due to the charge, then we get the force. So I didn't explain it that point of time because if you want to understand at that point of time, it would have been more complicated. So I skipped that. Okay, so now let's come to the electric field lines. So for a simple charge, right? For a simple charge, electric field lines will either be radially outward for positive charge or radially inward for a negative charge. So this is the property. Okay, this is a property. This you should remember. Always you should remember, electric field will be radially outward, going outward from the positive charge and going inward from the negative to the negative charge. Okay, it will come to the negative charge and it will go outward from the positive charge. If I have two charges, right, which are positive and negative, then what will happen? I will get a cylindrical locus. Basically, why cylindrical? Basically, charges will come out of this electric field lines will come out of this charge and it will be generated from plus q and it will terminate at minus q. Okay, few lines will generate and terminate at minus q because always electric field lines terminate at negative charge and generate from the positive charge. So this is an example of dipole. We will study about dipole, don't worry. These are equal, magnitude of charges are equal. Okay, magnitude of charges are equal. Magnitude are equal. Hence the electric field lines are also equal. Okay, Okay, electric field lines are also not equal. Fine. So this is our dipole. Sorry, they are equal as the magnitude is equal. If I have, let's say this is plus 2q and minus 2 minus q, so this will generate more lines than this can actually take. So here I will have more electric field intensity. Here I have less because this magnitude is lower than this, right? So that's why these lines will be lower here and lines will be higher here because the magnitude is more. So higher the charge, higher the magnitude. So electric field intensity actually depends on the magnitude of charge as well. Okay, this point I hope we have established. So we will do few questions. In the figure, the electric field lines for Q1, this is Q1 and Q2 are shown. We have to identify the sign of the charges. Both are positive charge. The upper charge is negative, lower is negative. Just pause the video and try to do it by yourself. We have to identify the sign of charges. Here Q1 we are observing that all the lines are terminating. Okay, all the lines are terminating. All lines are terminating for Q2 as well. For Q2 as well. And when does electric field lines terminate? Where does it terminate? It terminates at negative charge. So both of them are negative charges. So option A will be correct. Okay, so let's read more about electric field intensity. The tangent to the electric field line at any point gives the direction of electric field intensity that we already know. A positive charge placed at a point in the electric field experiences a force along the tangent of the electric field line. Okay, if a positive charge is placed along this electric field line, it will experience a force along this direction of the electric field. However, if released from rest, the charge will not necessarily follow a simple single field line. So what will happen is, let's say this is the electric field, right? Now if I place a point charge over here, you will say, okay, I will experience a force in this direction, and you will say I will follow along this line. No, it is correct that if I place a point charge here, I will initially experience a force in this tangent, right? But then again I will come here, and then again here some other electric field line will be there that will experience some other force in some other direction. So it is not necessarily true that if I place this point charge over here, it will go along this line. It will follow some other path. But what is sure, I know at this exact point the direction of the force will be in this direction. Okay, the direction of force will be in this particular direction. I hope you got the point. So let's come back to this point, right? Electric field lines can never cross each other and can never form closed loop. So they never can form closed loop or cross each other. If they can never form closed loop, right? If they can never form closed loop, so basically from this property I can directly say that del cross E will always be equals to 0 because it doesn't have any rotational effect to it. It is e-rotational. Electric field lines are e-rotational by property. Okay, because it doesn't have any rotational effect to it. I hope you got the point. Okay, and this also I told you the trajectory. Okay, and force direction I have already mentioned. Why electric field lines can never cross each other, I have already mentioned previously. Okay, I hope you understand. Basically, if they cross each other, right, let's say I have a field line in this direction and I have a field line in this direction. At this particular point, what is the direction of the field? What is the direction of the force that the charge will experience? You will say, sir, the charge will experience force in this direction. You will say charge will experience force in this direction. I don't know. Okay, I don't know. So it is ambiguous. So it is not possible for electric field lines to cross each other. So I hope you got the point. Now let's move on to the next discussion about electric field intensity. Intensity of electric field at a point is equal to the electrostatic force experienced by a unit positive charge. Okay, so if I have, like, this is the electric field intensity, like lines are going out, how much does this unit positive charge, this is q naught is a unit positive charge, how much does this force experience? So what will be the force experienced by q naught? It will be simply k is 1 by 4 pi epsilon into capital Q into q naught divided by r square, and obviously ar cap is already there. Ar cap is already there. Okay, so this is the amount of force experienced by this. Now what is electric field intensity? Here q naught is actually unit positive charge, we already know, unit positive charge. Okay, so what will be my electric field intensity? Basically what I will do limit as q naught is tending to 0. Okay, I will put q naught tending to 0 because I will assume I have no charge. F vector divided by q naught. Simply do this. So this will be equals to what? K q divided by r square ar cap. So this is the expression for a point charge, right? Electric field due to point charge. Electric field due to point charge. Okay, so now one more point we can notice is this actually depends on k as well. So if I write this, k is 1 by 4 pi. So electric field line is inversely proportional to the 1 by epsilon r, because k is 1 by 4 pi epsilon, not epsilon r. So for conductor, right, conductor, epsilon r is infinity. So electric field will be 0. So inside a conductor, the electric field lines will always be 0. So this is for a, we'll see this electric field for a perfect conductor, right, will always be 0. There will not exist any electric field. This I will prove as well. This I will show you in more details later on. Don't worry. Okay. So this is for a perfect conductor. Remember, this is for a perfect conductor, right? If the conductor is not perfect, there is impurity, then things will change over here. That also I will discuss. Now, force on a charge in an electric field. This we know already. We'll just revise. When a charge enters into the electric field, created by another source, it experiences a force due to the field. Okay, obviously it cannot experience force due to its own electric field. It cannot experience that because it is never cutting that. If q is greater than 0, positive charge, the force vector will be in the same direction as the electric field vector, as mentioned, right? Electric field is in this direction. If I place a plus q charge over here, it will experience force in the same direction. But if I have a negative charge, right, it will be attractive because this is plus, so it will be attractive. So obviously it will be, the force vector is in opposite direction to the electric field. So this is just you have to take care of, and this is the superposition format of electric field intensity. Don't worry about the vector. I have told you how to resolve things in vector without remembering all this. Just simple formula, k cube by r square, and you just write the direction. That's it. K cube by r square, write the direction. Don't have to remember all this. Just take a note of it that we may have a cubic format because this is not unit vector. To convert this into unit vector, I had to divide by extra magnitude. So that's why this became cubic. Okay. Electric field due to a point charge. The electric field due to a positive charge always radiates outward. Electric field due to a positive charge always radiates outwards. That I already know. Away from the charge. So as I move away from the charge, it will be only plus. It can never go negative. Okay. And if I am moving in the negative x direction, it will be more towards negative x. If I observe this charge, right? If I move in this direction, it will be more in this direction only. And if I move in this direction, if I just move this q naught, if I place this q naught here, electric field intensity will be in this direction. If I place q naught here, electric field intensity will be in this direction, but distance has increased, so this electric field intensity will reduce because I have a r square here. As r has increased, so this intensity will reduce. But if I place a q naught over here, which direction will my electric field intensity be? In this direction or in this direction? It will be in this direction, right? Always radially outwards. So if it is in this direction, it will be in minus ax cap direction. So that's why electric field intensity is negative if I move in the negative x direction, and it is positive if I move in the positive x direction. For a negative charge, just the opposite. It will be negative for a if I move in the, so it will be positive if I move in the negative x direction, negative if I move in the positive x direction, because it is attractive in nature. So if I just place a q naught charge, okay, if I just place a q naught charge and just move it all over the place, just along the x-axis. Okay, along the x-axis, same for this. So the variation of electric field intensity will be something like this. Now I have taught you the electric field intensity due to simply a point charge, but what will be the vector format? So one cube root came, right? Cube thing came there here, right? We actually got a cube thing. So how do I derive this? So if I have any point P, what will be the electric field intensity due to a point charge Q? Okay, if it is placed at origin. Okay, so if I have a point charge Q that is placed at origin, okay, so this will be basically electric field intensity will be What will be the direction? Direction will be radially outward, so it will be in the AR cap direction. Remember AR cap. So what is AR cap basically? AR cap, I will just write this first. It will be K Q by R square. R square is the magnitude, the distance from this, magnitude whole square, into AR cap. So what is AR cap? AR cap is R vector divided by the magnitude. Okay. So can I write this further? What is R vector? R vector is the position vector, that is xi cap plus yj cap plus zk cap. This is the R vector, if you remember perfectly. This I have taught previously as well. And the magnitude will be x square plus y square plus z square whole under root. So what is electric field intensity in terms of x, y and z? So I'm just keeping you accustomed with all the formats so that you don't get scared if you see any of this format in the examination hall. So this will be kq, and this AR cap I will replace with R cap divided by magnitude. So magnitude of R is, so this actually becomes whole cube, right? This actually becomes magnitude of R cube into R vector, as written here, as it is written over here. Just same thing, just this is due to multiple charges, not single charge, multiple charges. Distance will also change. So I can further write this in terms of x, y and z. This will be xi cap plus yj cap plus zk cap. Do you notice one thing? That is R vector, right, actually has all the information about x, y and z that I taught you during unit vector conversion, right, for spherical coordinate system. So that's why for position vector I only need R vector, right, AR cap. So this will be divided with, what is magnitude of R? Magnitude of R is this under root. So I will take the cube as well. So this will become, just hold on, three by two. So if you see this format as well, this format is also correct. This is not incorrect. Okay. So I hope you get the point here. Now electric field due to group of charges, it will be simply, it will just follow superposition, just same as the force concept, right? Same. Now nothing to explain over here. Okay. It will be simply vector sum. Okay. It will be vector sum, not scalar sum. Electric field intensity is a vector quantity. Three identical point charges as shown are placed on the vertices of an isosceles right angle triangle. Which of the numbered vectors coincides in the direction with the electric field at the midpoint of M of the hypotenuse? So three identical charges are, okay, three identical point charges are shown. Okay, they should be actually, three identical point charges should be in the vertices, placed at the vertices. Okay, so here identical point charges, right? So this will be Q, this will be Q, this will be Q. Okay, three identical charges. So what will be the direction of electric field? Direction of the electric field will be same as the direction of force. If I place a positive charge over here, let's assume all of them are positive. So if all of them are positive, the force due to this Q and force due to this Q will basically cancel each other out. Only the force due to this Q, right, will be present. Okay, only the force due to this Q will be present. Now there are two things. What is the direction of electric field? It depends on the sign. If this is positively charged, right, if all of these are positively charged, so it will be always radially outward. So the direction of the sign will be 2. Okay, so 2 will be correct for electric field because these two components will be simply cancelled, right? If Q is positive, if Q is negative, direction will be inwards, right, radially inwards. So 1 will be correct then 1 will be correct if Q is negative. Now it depends what is the charge of Q, is it negative or positive? Okay, so that is the thing, 1 or 2, correct? So you have to understand whether it is positive or negative, right? Two options can be, this can be MSQ. Now let's do another question. So 2 point charges 5 into 10 raised to power minus 19 and 20 into 10 raised to power minus 19 are placed 2 meters apart At what point on the line joining them is the electric field 0? Okay, similar question, but this time we have to solve electric field, not force. So I have 2 point charges. This is let's say q1, and this is, let's say, q2. Okay, the distance is 2 meters. At what point will the electric field be 0? So I will assume a point. I will assume this point, let's say this point, where the electric field is 0. So this distance, let's assume this as x. So this whole this remaining distance will be simply 2 minus x. So basically here electric field intensity will be, basically at this point, what will be the electric field intensity if I place a positive charge here? Due to this q1 it will be in this direction, due to this q2 it will be in this direction, right? So both of them will cancel each other out. So due to q1 it will be kq1 divided by x square minus, I have already taken the direction into effect, kq2 divided by 2 minus x square. So now what I can do is, this has to be 0, right? Electric field has to be 0. So kk will get cancelled. q1 by q2, this will go here, this will come here, will be equals to x by 2 minus x whole square. If I take the under root, so this actually becomes q1 is 5, right? So q1 is 5, so this will be 1 by 4. If I take the under root, this will be 1 by 2 x by 2 minus x. So 2 minus x will be equals to 2x. So x equals to 2 by 3 meters. Okay, x equals to 2 by 3 meters. So yeah, this will be the answer. Basically at this particular point the electric field will be 0. Electric field will also be 0 at some other point as well, where it will be 0. If this is negative, let's say this is one of the solution. If let's say this was negative, right, minus 1 by 2 minus 2x, this will be minus 2 plus x equals to minus, not minus, plus x plus 2x, right? So this becomes x equals to minus 2. Now x equals to minus 2 meaning what? Somewhere here, right? At x equals to minus 2 also the force will be, electric field, it will be 0. But at what point line joining them? They have asked line joining them. So as line is joining them, it should be between q1 and q2. So obviously we'll pick this as the solution. Okay, x equal to 2 by 3. But this can also be a solution. This is not wrong. Okay, but this will ignore because they have asked line joining them. Okay, so this is the solution. Let's move on to the next question. So here 2 point charges A and B have equal magnitudes and are placed at certain distance from each other. So 2 point charges A and B, QA, QB, and their distance is what? Distance is basically some d distance, right? Given that the electric field strength is considered positive in the direction of the positive r axis, basically on the line joining them, that is what they are talking about, a positive r axis. Determine the signs of the charges based on the field strength distributions shown in the figures A to B. So what will be the signs of the charges? Okay, so here, right, what it is telling us is that in the first case, what will be the sign of a QA and QB if the electric field intensity is varying like this? If I place a test charge here, the electric field intensity is like this, very high. Then again I move out, and then again it is very high. So during this whole duration, right, the electric field intensity is radially outward. If I place a positive charge here, the electric field intensity is in the plus positive direction, right? Plus r direction, very high. Why high? Because this plus q naught, right, will be very near to the QA. Hence the distance is very small, hence the electric field will be very, very high. But this is in the positive r direction. So here I can observe for the case A, electric field is always positive, okay, in AR cap. So obviously this has to be positive, this has to repel, and this also has to attract, right? This has to also attract. Or what I can say, although the signs, although this can also be positive, but this is bigger. This has to be bigger than this. Okay, this has to be bigger. This has to be positive first of all. At least one of them has to be positive, or Q1 has to be higher than Q2. If QA is higher than Q2, QB. Okay, yeah. Basically, although I cannot directly comment about the signs, but what I can comment is, for the case A, QA will be greater than QB. Why? Because electric field is always positive. Now if I assume QA to be positive, then like that's done, right? QB can be negative as well, it doesn't matter. But okay, if QA here, right, if it is 0 somewhere it will go 0. Okay, here electric field is always positive, that means QB also has to be negative because it is always positive. If let's say QB was positive, let's say one thing is, let's say QB was positive. If QB was positive, if I come here, right, the electric field will be in this direction because this will dominate. Why this will dominate? Because the distance from QB to this test charge will be very low. R will be very low. Hence the electric field due to B will be dominating. Hence it will be readily outward, that is in the negative x direction. But it is not the case, right? It is positive. That means QB also has to be negative. So QB also will be negative. QA is 0. QB also will be greater than 0. It will be positive. What about the B case? As I am moving away from the A charge, right, the positive electric field intensity is going towards 0 and then coming back to negative. So from here to here I can assume that electric field due to A is dominating, right? Because obviously the more near I am towards A, the electric field due to A will dominate, as the distance is very low, which is readily outward, which is in the positive x direction. That means Q1 has to be positive. So electric field near QA is positive. Hence QA will be greater than 0, and electric field near QB as it is dominating is negative. Hence QB will be 0. Less than 0. Okay, next come to this problem. Here electric field near QA is negative, electric field near QB is also negative. So obviously what I can say is both of them will be negative itself. Both of them will be negative simply. Okay. This will also be negative. Okay, so for the fourth case, what is for the fourth case? Fourth case, just this will flip. Due to A it is negative, that means it will be QA will be negative, and due to B it is positive, that means QB will be positive. So this will be flipped simply. QB will be greater than 0 and QA will be less than 0, right? Okay, so that is the case over here. So I hope you enjoyed this problem. This is a very good problem. Now let's do this problem. 2 point charges are positioned on x-axis, okay, plus A and minus A, at plus A and minus A respectively as shown in the figure. Plot the variation of electric field along the x-axis and plot the variation of electric field along the y-axis. So this is a very good question, right? So if I place a charge over here, we just solve this particular case, right? If I place a charge over here, what will happen? Electric field due to this will dominate, right? Although this is also getting attracted. This is a, let's say, I will just take this, paste this over here. Okay, if I just place a point charge over here, right, of Q0, so electric field due to this plus Q will be radially outward. Electric field due to this minus Q will also be in this direction itself. Again, if I come at this point as well, electric field will be in this direction only, but it will be very high, right? This will be very high. If I am somewhere in the middle, so the r square distance with both of them becomes very high, and the electric field reduces. So basically, due to x-axis, right? Due to x-axis, the electric field will be something like this. Once it is very near plus q, then again it will be somewhat lower, but still there will be some field. Then again it will be very near minus q, and then again it will increase. Okay. So this is about the x-axis. This is about the x-axis. Okay. So this is for the A case. For the B case, things are a bit interesting. So I have to find the electric field along the y-axis. This is not y. This is E. Okay. This is the x. So here what will happen? Here, right? If you observe, actually here, if I place a plus q naught charge here, what will happen? The electric field will be in this direction, that is in the negative ax cap. So it will be somewhat like this, right? It will be discontinuous. Electric field intensity will be discontinuous. So it will be very high, and then again it will come to 0. Okay, graph will be something like this. Here as well, the same thing. If I place a q naught charge here, what will happen? If I place a q naught charge here, it will actually attract it. So it is again in the negative x direction. So again it will be something like this, very high, and then again it will die down as the distance becomes very high. So this is a very, very interesting graph. Okay, people solve the graph until this, they don't solve the graph here. So this is also important, right? What about the y-axis? So about the y-axis, right, just do with intuition. What intuition? If I place a q naught charge here, what will happen? The force due to this plus q, right, will be in this direction. The force due to this minus q will be in this direction. So overall, if I break this down into components, in vertical and horizontal components, this components will get cancelled. Only this y component will be present. So y component is what? This is getting twice. Okay. But okay, sorry. This is getting in this direction. No. Sorry, I have made a mistake. Just hold on. So if I place a q naught charge over here, this electric field will be in this direction, as force is in this direction. If due to this, the electric field will be in this direction. Okay, electric field will be in this direction. So the electric field will be actually along the x direction. So if I keep on varying here as well, again this distance will actually increase, because this distance has increased, and the y components will be cancelled. Only the x component will be there. I am more concerned about the magnitude of electric field. So if I am varying about the y-axis, okay, of the electric field of the test charge, what I will observe is, as I move away, right, distance increases. As the distance increases, what will happen? Electric field intensity will reduce. Okay, and at origin, I will get the lowest distance, because here the distance, let's say this is a and this is a. Here, right, the distance will be somewhat greater than a, right, somewhat greater than a, and all of the charges are actually not acting here. So here, right, what is the electric field intensity? This is giving me in this direction. This minus q also is giving me in this direction. But here what is happening? This electric field intensity is in this direction, and due to this minus q in this direction. Okay, and basically I have to break it down into components, because two components are cancelling, the y component part, and the x component is remaining. So at the origin I will get maximum, and then again it will die down. Okay, so basically what will happen? I'll keep this q naught just for visualization purpose. It will just die down, right? Now this is not the electric field in y direction. This is just the electric field, okay, on the y axis. Okay, electric field, variation of electric field on the y axis. Okay, this is the case. Okay, so these are very, very good questions. If you couldn't understand, please rewind and see it again. Now we will understand electric field due to continuous charge distribution. So how do we find electric field due to continuous charge distribution? In case of continuous charge distribution, what we do is, like, I know how to find electric field intensity due to a point charge. So I will break each distribution into small particles that will be consisting of point charges, and due to that point charges, I will compute the electric field intensity, and I will totally integrate it over the limits, and I will get my electric field intensity. Okay, how we do that, I will obviously show you with examples, but this is the crux of what we do. So I have already explained what are different charge distributions. So inside charge distribution we have discrete charge distribution and continuous. Discrete means they can be separated in terms of point charges. Continuous means I cannot separate them. And inside continuous also I have two types. One is finite and infinite. What do you mean by finite? Is I can at least count how much charge I have, right? I can count it. But in case of infinite, right, I cannot count. Total charge will be infinity. I will show you that as well. Don't worry. Okay. So if I have an infinite line charge, because this is extending in throughout the whole z axis, I cannot count what is the total charge on this particular rod. If it is finite, then it will be q. If it is finite, okay, is it finite or okay? This should be this can be infinite or finite as well. If this is finite, the total charge will be q. If this is infinite, I cannot say what is the total charge, because this will be a rod of infinite length, and I can only define the line charge density, that is charge per unit length. Okay, charge per unit length I can define for infinite line charge. If it is finite, I can define the total charge on the rod. Okay, that I can define. And do remember this dq is actually with sign. Okay, you have to remember this dq actually with sign, and dl obviously is always positive. Length always will be positive. Length will be always positive. And there is another finite line charge distribution, that is ring charge. Okay, so this is ring charge basically. If this is ring charge, this is in the x direction, this is in the y direction. So now what will happen is that, how do I find out the total charge on the ring is q, that is fine. How do I find the charge per unit length? That is dq upon dl. So how can I define dl? Dl is length, right? So how do I find out dl? So if I just move this by theta theta angle or d phi angle, I will get my dl basically. So here this is, I'll move this by d phi angle. So this angle will be r, or I can say this is rho actually, in this case r. So I can say this radius is of r actually, the radius of r. So this will be r d phi. Okay, so dl I can write as r d phi. So this will be dq upon r d phi. Okay, so this is how you can resolve this. And again, the total charge, how can you derive the total charge? Total charge can be equals to rho l integration of dl over the whole number side. If you integrate this, you will get the total charge for a finite charge distribution. For infinite, obviously charge is infinity. Okay, now if this particular case is of uniform charge distribution, uniform charge distribution means my charge density will be constant. So if charge density is constant, I can simply divide the total charge by its length, and I will get back my line charge density. So total charge divided by length. Okay, that is how I will get my line charge density for uniform charge distribution. Rho L will also be q by 2 pi p. Okay, 2 pi p, or this is like radius p, that's why p, or you can write it as r as well. Okay, now just a short thing that you need to remember for line charge distribution is that line charge density is defined as dq upon dl. Dq can be written as rho L dl. Okay, if I integrate this over the whole length, I will get my whole charge. If it is uniform, rho L will be constant. I can take it outside of the integration, as rho L will not be a function of L, it will be constant. And if it is non-uniform, then I have to write this rho L in terms of x or length L, then only I will be able to find the total charge. Okay, so we'll do one example problem, this one. Compute the total charge on the rod for the following configuration. So lambda, that is the charge per unit length. This is charge is coulomb per meter. So in units, you have to observe the units as well to identify what this is exactly is given, and length is also given. You have to find the total charge. How to find the total charge? Simply q is equals to rho L dl, right? As this is only on the x direction, this is only on the x direction. Okay, this I should have written ax cap, right? So dl, so what will happen is this will be 10 e raised to power minus x ax cap dot ax cap, right? this will be sorry, this will be dx ax cap plus dy az cap, all those things will be there, but all those dot products will be simply 0. So here x will be what? X will be going from how much? X, I'm going in this direction. X is from 0 to L, right? 0 to L. So actually I should have mentioned that this is at x equals to 0 actually. Okay, I should have mentioned this. This point is at x equals to 0. So this will go from 0 to L is how much? 2 meters. So this will be 10 e raised to power minus x dx. So this will be minus e raised to power minus x 0 to 2. So this will be 10 into 1 minus 1 minus e raised to power minus 2. Okay, so this will be your answer. Basically this will be the total charge q present in the rod. Okay, so this is not uniform, so we have to use the generalized method. So let's identify few charges basically. So if we identify few charges, I will try to find the electric field intensity due to a ring charge. Okay, due to a ring charge. So we'll derive few things. Just derivation is good, but you have to, at the end you have to remember the formula, but derivation is good just in case in the examination hall you have to derive something new. Okay, it is good. So from the axis, on the axis of the cylinder, I have to find out from the axis of the cylinder. So what is happening is, if I place any point P here, any Q naught test charge Q naught here, this is uniform. Okay, this is uniform. So first of all we have to say this is, I am talking about uniform only, because non-uniform case deriving will take years. Okay, not years actually, but it will take huge time. Uniform distribution. So here one thing I can observe, the field due to this dq, right, small charge here, let's say there is some small, like this is totally uniform distributed, right? If I take this area, due to this area will be in this direction, and due to this area will be in this direction. So what is happening, the y components are getting cancelled. Okay, the y components are getting cancelled. So let's say this is dq and this is dq dash. If I take very small charge dq here and dq dash here, what is happening, the electric field due to this will be, electric field due to dq will be in this direction, and electric field due to dq dash will be in this direction. Okay, okay, will be in this direction. Okay, this is d dash, right? So basically what is happening, the y component will get cancelled. This is symmetrical, so y component will get cancelled, only the x component will be remaining, only the along the x axis. So what will happen here is, what is the electric field dE due to this small charge? This I can assume as point charge, right? So electric field dE on the test charge due to the small charge dq will be what? It will be dq k dq divided by r square. What is the distance? This is the distance, right? That is x square plus capital R square. This radius is capital R, so it will be x square plus r square. This is the magnitude. I am not talking about the vector right now. I am not talking about the direction right now. Okay, so this is the electric field. Now what is the x component of the electric field? Dex. What is the x component basically? Because I am only interested in this direction, because in the y direction anyways it is getting cancelled. X component will be this cos alpha, right? dE cos alpha. This angle is actually alpha. This angle is alpha because angle, and I can find out this angle easily. This angle is alpha, so it will be dE cos alpha. So what is cos alpha basically? Cos alpha, it will be dE cos alpha is basically this, right? Base upon hypotenuse, so it will be x by r. Okay, x by smaller. So if I do this here, my dex, right, dex, which is what I'm interested in. Okay, because dy will anyways get cancelled. I am not consider, like I don't care about that. Dex will be, small d is k dq into x by r. Okay, r is under root x square plus r square, so this whole thing will become x square plus r square. Okay, so now what will be the net electric field? What will be the net electric field? The net electric field, basically I will not do 2 times this, because just I'm identifying due to this dq, right? I will rotate throughout this whole axis. I will rotate a whole angle of 2 pi and I will compute the net electric field. Okay, if I rotate a whole angle of 2 pi, how much charge will I cover? Q charge, right? How much charge will I cover? Q charge. So E net will be the overall integration of dEx, right, in the ax cap direction, because I already know the direction, right? I have already assumed the direction. Okay, so this will be simply equals to x integration x divided by capital R square plus x square 3 by 2. K is also there. Okay, k is also there obviously here. Okay, and dq. Can you tell me what is the variable? Is x the variable? X is not variable, right? X is constant. X is constant. Why? How is x constant? Here, right, x is constant, right? Here is x constant, because I am just like, this point is fixed. This point is fixed. What is varying? I am varying here, right? The angle is varying. I am covering the whole charge. Okay, from dq to total charge. So charge from 0 to q charge. So this is, all of this is constant simply. So overall the expression becomes very, very simple. E net is in the ax direction, that is k x divided by r square plus x square 3 by 2 into ax cap. So I hope you understand that what is happening over here, right? I hope you understand this point. This is very simple derivation. So this have been written already here. Okay, I have already written it over here. So if this q only for uniform charge distribution, this is not valid for non-uniform charge distribution. So the vertical component of the electric field produced by a charge is cancelled out by the electric field from a charge placed diametrically opposite to the original shape. So if I place a charge here, these charges, right, will cancel the vertical components, only the horizontal components will remain. So I am not taking twice of the horizontal components, because I will again come back here. I don't need to take this extra. I will come back here. Don't worry about that. Okay, so E net will be this, and if it is given in terms of charge density, so I can write q as what? Q as rho l into 2 pi l, right? Rho l into 2 pi l, and if I 2 pi r, if the radius is r, and 2 pi and this 4 pi will get cancelled. This will be rho l by 2e 2 epsilon, and this will be the expression. This expression will be same. Now let's do a quick sanity check. Let's do a quick sanity check. If I put x equals to 0, if I put x equal to 0, x equal to 0 means center of the ring. So at center of the ring, what will happen? This is a regular shape, geometric regular shape, and at the center of a regular shape of a uniform charge distribution, the electric field will be simply 0, because all these charges will, this charge will provide force in this direction, this charge will provide force in this direction, in this direction, in this direction, and all of them will cancel out, and it will be simply 0. Okay, it will be simply 0. Okay, so basically this is correct, right? If I put x equal to 0, this whole thing goes to 0. So this is correct. E net is 0. Okay, so that's how we do it. Now there is a variation of field charge due to ring. The variation of electric field intensity due to ring charge. As x increases initially, the numerator will increases more significantly than the denominator. Then after a certain point, that is this point, that is the radius divided by root 2, the electric field again reduces. Why? The function is like this only, because what is happening is that I have x and x square here as well, right? So initially this will dominate, and after that this denominator will dominate as the higher values of x. So towards the end, electric field will go 0. Again at origin, electric field will be 0. Basically, if I just copy this thing, okay, at origin it will be 0, near somewhere in the middle it will be very high, then again towards infinity it will be 0. Again on the left hand side also same, it will be symmetrical about the x-axis, about the what do you say, about its own vertical axis, right? So yeah, E net is this. If let's say if this ring charge was placed in z direction and on a height r, okay, on a height r or h, everything will be same, okay, just this point, right, the distance from this point will change. Now this won't be x anymore, this will be x minus r. Here we are not talking about x because this is on the axis of this ring is z axis, so this will be z minus r. Just replace z with z minus r. Why? Because it is also above the z axis by r. So I replace everywhere, wherever there was x or z present, I will replace it with z minus r. That's it, nothing else. I have changed nothing. So this is the other format because the distance has reduced now. Previously it was total z distance, now it is z minus r because this is also above the z axis by r distance. Okay, so this is the case. Okay, so let's go to the next like question. A circular ring carries a uniformly distributed positive charge and lies in the yz plane. Okay, it is lying in the yz plane. So so the electric field will be on, obviously on the x direction or along the axis. If at a point x, 0, 0, electric field is E, which of the following graphs is correct? So basically I am varying through x. Okay, I'm varying through x and I am measuring the electric field intensity. So what you know is electric field intensity. I have already shown you the graph. Okay, the graph will be somewhat like this, right? It cannot be this because at the center it is telling electric field intensity is 0. Fine. Here if I have a ring charge here, right, this, here it is readily outward, here as well it will be readily outward in the negative x direction. So it cannot be positive on both ends, it has to be negative and positive, but this is not possible because this could have been possible if this was a positively this was a negatively charged. So to mention positive, they have mentioned positive, right? They have mentioned here positive. As this is positive, so it will be always radially outwards. Okay, radially outwards. So option B will be correct. Basically I have already shown you the graph, and this cannot be always negative. Okay, it has to be positive on one end and negative at the other end, as it is radially outwards. And at what point it will be maxima? I have already mentioned this, that it will be P by root 2. The homework for you is you find out this point by yourself. What you do? You differentiate electric field with respect to x. Okay, whatever I have derived, you differentiate it with respect to x, then put it equals to 0, and then from there you will find the value of x. Okay, so that's how you find it out. Now if I have a arc charge, right, if I have an arc charge, then how will I find out the electric field? So electric field due to arc charge, how will I find out the electric field due to arc charge? So electric field due to arc charge will be lambda charge per unit length, radius of arc, angle of arc. Okay, so electric field due to arc charge will be same, just the difference will be here my theta won't be from 0 to pi, right? Because basically this whole thing is covering getting the q charge. Because if you observe again, if I take this dq charge, right? Let's take this dq charge. Due to this dq charge, I will get some electric field intensity, and due to this dq dash charge, I will get some electric field intensity, right? So overall, what will happen? Here and here, both of them will get cancelled. Only it will remain on this end, right? So that is the thing. So that is what I will do. Again, along the axis, the electric field intensity will be existing. Okay. So what will be this? dE will be equals to k dq by r square, right? Due to small electric charge. Okay. What I know is that this electric field, only this will get cancelled, right? Okay, so how will I compute it basically? So here what I can do is I can write this, right, due to this dq at this end, the angle from the normal. Okay, this is this angle, right, and this angle is the same only. So extend this angle and this angle will be same. So this will be theta basically. So again dE is this, dE, I will write it properly. dE is kq dq by r square, and I need to find out the angle along its electric field along its axis. So DE along its own axis, right? X will be simply DE cos theta. Okay, because this is the theta angle, this is also theta, cos theta. So it will be DE cos theta. So what I can write, that DE will be like E net will be simply integration of DE, that is DEX itself, right, which is DE cos theta. So what is cos theta? Basically cos theta is I don't know what is cos theta. Cos theta, like it is alpha angle, it depends on this arc angle, right? So basically this time, right, it is K dq by r square. I will integrate, and what else can I do? R d theta, right? Dq actually, okay, what is dq actually? What is dq? How can I define dq? So if I know the charge per unit length is lambda, so lambda into dl or r d theta will be equals to dq, right? Correct, because dl is what? R d theta. dl is r d theta. So if I multiply lambda with r d theta, I will get dq. Okay, so I will replace dq with respect to r d theta, lambda r d theta, because theta is variable over here, and I have a cos theta as well, right? Cos theta. So I'll write the cos theta somewhere here, and theta is varying from, like, if I am lying at this point, okay, theta will vary from this, let's assume this angle. What is this angle? This angle is minus alpha by 2 to plus alpha by 2. If this angle is 0, this angle will be minus alpha by 2 to plus alpha by 2. Here this angle is 0, right? I'm rotating this whole vector, so if I'm lying here, this angle will be 0, theta will be minus alpha by 2, so not 0, this will be minus alpha by 2, here it will be 0, and here it will be plus alpha by 2. So I'll go from minus alpha by 2 to plus alpha by 2, not 0, sorry, minus alpha by 2 to plus alpha by 2. So if I go from minus alpha by 2 to plus alpha by 2, what will I get? This will become E net, right? E net will be magnitude of E net. Actually direction will be along the radial direction, so more interested on the magnitude. So this will be sine cos theta will be sine theta, and this will be, yeah, minus minus will become plus only, so this will be 2k lambda, r will get cancelled, 2k lambda by r sine alpha by 2. Okay, 2k lambda sine alpha by 2. So this is actually a pretty important expression. It's good to remember. You can obviously derive it, it will take you seconds, but it's good to remember. This is actually a pretty important expression. So this question, in a cylindrical coordinate system, the potential produced by a uniform ring charge is given phi as a function of r and z. Okay, we know what is the electric field intensity given by a uniform ring charge, right? Okay, where f is continuous function of r and z. E be resulting electric field and magnitude of del cross E. What is the magnitude of del cross E? What is del cross E? I know, right? Electric field, I have already told to you that property of electric field is E rotational. E rotational. If electric field is E rotational, then that means del cross E will be 0. Okay, hence the magnitude of del cross E will be simply 0. Simply 0. So option B will be correct. You don't have to even calculate anything. This is very simple. Option B will be correct. So yeah, that's it basically for this lecture. And in the next lecture, we'll see more distributions of electric field intensity and we'll solve more questions, right? Thank you for watching and happy learning.